Okay, so we're back. We were in the middle of number 2 here. 1.7 squared, remember that's not 1.7 times 2, it's 1.7 squared. So that is going to be 2.89, and then we multiply next the 4.5 to get 20, and then we just have addition and subtraction from left to right. Subtraction comes first, so we go across and we get that. And we end up with negative 11.11. Okay, and the third one, when we look at the parentheses here, we can see that we do have something to do in the parentheses, okay? We have to add these two fractions. So I have that work over here on the side. I made common denominators and then added those fractions together. And then in the next step, we have to square this. So remember, 7 over 6 squared means 7 over 6 times 7 over 6. I multiply across the top and the bottom. I get 49 over 36. We now also have a root here, so that happens with the same level as exponents. So we did this one first because it came first left to right. Then we do square root of 16 as 4. In this step, I also wrote 36 as 36 over 1. And just to remind you that it's a little bit easier to multiply two fractions if they're both written as fractions, right? So then here I can choose to cancel out a common factor of 36. They both become a 1. So I get 49 over 1, which is just 49. 5 minus 49 is negative 44. Negative 44 plus 4 is negative 40. And then for this last one, it looks a little more complicated, okay? But again, just take it step by step, remembering our order of operations. So we're going to do parentheses first. Again, there is an operation to do in the parentheses. There are actually two operations. There's subtraction and an exponent. So we do the exponent first. Anything to the 0 power is 1. That's all I did in this first step, is I just changed that. And then in the next step, negative 9 minus 1 becomes negative 10. Then here I have addition, division, exponent, multiplication, addition, and then I still over here have these grouping symbols, okay? So negative 30 plus 5 is negative 25. This absolute value I would do next to become 25. So at this point, I've just taken care of the parentheses and the absolute value. Well, now I look, I still have exponents. So I'm going to take my exponent, 2 to the third power. 2 times 2 times 2 is 8. That's what I do in this step here. Now here, it's very tempting to want to multiply this first, because the 8 and the negative 10 are kind of cozy with their parentheses, right? But we have to remember that order. Multiplication and division happens left to right. So I actually am going to do this division next. So 24 divided by 8 is 3. And then in the next step I can multiply, and then I add from the left to the right, negative 7 plus negative 30, and then add the 25. So again, any of these you're not sure about, pause the video, kind of go through the steps, watch it again if you need to, and then certainly ask me. So one of the things about studying math is that you always need to make sure you understand how we got from one step to the next. And if there's any little part that you're not sure of, you need to make sure you ask about it or look it over again until it, makes sense to you, because otherwise that means that you can't do that problem completely on your own. Okay, so just really make sure you can understand that. Okay, let's move down here. So I started to do this on the video and then I closed it by mistake. So that's why some of this is written in already, but I'll just talk through it again. So we're going to talk about multiples and factors. So when you count by a number, the numbers that you get are called multiples. So if I'm counting by 3, I would say 3, 6, 9, 12. I would get multiples of 3. So these are also called multiples because you're multiplying integers by them. So 3 times 1, 3 times 2, 3 times 3, 3 times 4. That's how you get these multiples. So we list some multiples of 5. We list some multiples of 26. It asks for 4 of them. So I just put the first 4, the smallest 4. It doesn't really matter which ones. But how do I get multiples of 26? Well, 26 times 1, 26 times 2, 26 times 3. I didn't know that, so I did my work over here. 26 times 4. I didn't know that, so I did my work over here. I could do 26 times any integer if I did 26 times 15, whatever that answer is would also be a multiple of 26. It would be in that list of counting by 26s eventually. Can I ask you to write out all of the multiples of a number? No. There are an infinite number of them. If I said count by threes and just keep counting, you would be there forever counting. Because if you got to 3 million, you could say 3,000,003, 3,000,006, 3,000,009. You could always just add another 3. But we look at factors. Factors are the numbers in the multiplication facts that make up that number. So what are all the factors of 24? Okay, now when I say multiplication facts here and factors, we just want integer factors. So I don't want to know in this list 2.5 if that's a factor, right? I just want integers. So what we want to do here is we want to think of things, numbers that multiply together to make 24. So one thing I could do is I could ask everyone in a room to just call out some answers that are factors of 24. So someone might say, oh, 1 times 24 makes 24. Someone else might say 4 times 6 equals 24. And those are right, but if we're just sort of doing it in a not very organized way, we don't know that we've gotten them all, right? And we need all the factors. So if I want to find all the factors of a number, I suggest doing it this way, because this way you'll know that you have them all. So what I suggest doing is starting out in order with 1 and seeing if 1 is a factor of 24. So 1 times 24 makes 24, okay? Then I go on to 2. Now if I don't know if a number is a factor, I'm going to use my calculator and divide. I'm going to say 24 divided by 2, and whatever I get is going to be the other factor if it's an integer. So if I take 24 divided by 2, I get 12. So 2 and 12 are both factors. If I take 24 divided by 3, I get 8. If I take 24 divided by 4, I get 6. Now, if you take your calculator for a minute and take 24 and divide it by 5, you'll get 4.8. That means that 5 is not a factor because you do not multiply it by another integer to get 24. So we don't want to put 5 in our list. Well, then I can go down and put 6 in my list. Well, that way, if I did 6 and I'd have 4, I'd have a repeat, and I don't want any repeats. So once I have all of my numbers in here that I can, once I've gone down the row in order, included any number that is a factor, and once I start getting a repeat, that means I've gotten all of the factors of 24. So let's try this larger one, 26. Okay. Or sorry, 260. So I don't know all the factors of 260 off the top of my head. So I started doing this before I mistakenly turned off the video. So 1 goes into 260 260 times. I know 2 goes into it because it's even. So if I do 260 divided by 2, I get 130. Now, I'm not going to pull up the calculator on the screen again because when I did that last time, that's how I turned off the video by mistake. But I just have my calculator over on the side next to me here, and you can do the same. So 260 divided by 3, I get 86.666666, 86.6 repeating. So that is not a factor. 3 is not a factor. If I do 4, I get 65. If I do 260 divided by 5, I get 52. Again, I don't know these off the top of my head. I am looking at my calculator, okay? 6. So let's see, 260 divided by 6 gives me 43.3 repeating. So I do not want that in my list. I shouldn't have written it quite so quickly. 260 divided by 7 is a decimal also. If you look at that, just to kind of look at something here, if I look at 260 divided by 7, what I get looks sort of random. So you might glance at it and say, wow, that almost looks like an irrational number, which it can't be because it could be written as 260 over 7. But it looks kind of crazy. But if you look at this carefully, the decimal part, it's actually repeating. It just repeats more than one number. So it's 142857. 142857. So we could actually write this with the repeating sign. You don't often see these in our level of math here, but that whole thing is repeating. Okay, so it's just kind of an extra little nugget of math information there. Okay, so 7 is not going to be on our list. How about 8? 260 divided by 8 is 32.5. That's not going to work either. 260 divided by 9 is also a decimal. 260 divided by 10 is 26. Finally, we get something else that works. So now we keep going. 260 divided by 11 is a decimal. 260 divided by 12 is a decimal, so I don't include those. 260 divided by 13 is 20. 260 divided by 14, again, if you look at that, that is another long repeating decimal, 0.571428. 260 divided by 15 is a decimal. 260 divided by 16 is a decimal. Same with 260 divided by 16, by 17, by 18, and by 19. So 260 divided by 20 is the next thing that will be a factor, but I already have that. So now I have all of my factors of 260. Okay? And we're going to be doing some things later on in the semester, especially what we call factoring, where we need to have all the factors, because if we miss a pair, that might be just the one we need for our problem. So we need to have this way to find all of the factors. What factor does every single number have? Well, every single number has the factor of 1, okay? And also, every single number also has itself as a factor, because 1 times itself is that number. So let's kind of look down here. We have a prime number is a number whose only factors are 1 and itself. Can we list some prime numbers? Well, let's list some. I'm going to give you a list here. 2, 3, 5, 7. Okay, now it's tempting to say 9, but it's not 9 because 3 times 3 is 9. That's a factor of 9 that's not 1 or itself. Let's see, so the next one is going to be 11, 13, not 15, because 5 times 3 is 15. So here's a small little sampling of prime numbers. They go on forever. Really big prime numbers are used in encryption, like on the computer when things are sent encrypted. Some of that involves really, really big prime numbers because they're hard to figure out in an expression. If you look at this, 2 is the only even prime number, okay? Let's think about why that is. Well, 2 only has 1 and 2 as factors, okay? Any other even number is going to have 1 and itself as factors plus 2 times something. It might have more factors also, but any other even number is always divisible by 2. So it's always going to have not only 1 in itself, but also 2. So therefore, this is going to not be prime, right? Any other even number is going to be what we call composite. So a composite number is just the opposite of prime. It's a number that does have factors other than 1 in itself. So, for example, 4, 6, any even number above 2, but also some odd numbers, like we said, 9. Let's see, so we missed 8 here. Let's turn this into an 8. 8, 9, 10, not 11, but 12, 14, 15. Okay, so again, a little sampling of some composite numbers. The number 1 is neither prime nor composite. So the number 2 is also, not only is it the only even prime number, it's also the smallest prime number. Okay, the prime numbers do not start with 1, they start with 2. So prime factorization, we had talked about this in one of the classes last week. Prime factorization is the unique set of prime numbers that multiplies to make a given number. Okay, so when we looked at all the factors before, we were looking for any 2 numbers that multiply to make that given number. So for example, 4 times 65, 10 times 26, 13 times 20. Any numbers. Some of these are prime like 2 and 5 and 13. Some are composite, like 4 and 10 and 65 and 52, okay? Those are all composite. So it didn't matter which we wanted. So finding the prime factorization is a different question here. And if you're watching the time, you might have noticed I'm over 15 minutes, but that's because after the last break, I was tired of getting cut off, so I got the next little upgrade to this program, so now I can do more than 15 minutes. Okay, so prime factorization is the unique set of prime numbers that multiplies to make a given number. So basically, what we want to do is we want to break down any factors into their smallest little building blocks. I always picture Legos for some reason. We want to break it down into the smallest possible chunks that we can. Okay, so we're going to use a factor tree, which most people kind of remember. If you don't, that's fine, but we're going to use a factor tree to find our prime factorization. So here's what we do. We're going to start with the number we want to find the prime factorization for. And we're going to split that up into any two factors of 150. Okay, I don't care what it is, but that's what's going to go here. So I might say, okay, I know 15 times 10 is 150. You can use your calculator to divide until you find a pair of factors. Now I break these down, each of these down further. So how can I break 15 down? Well, it's 3 times 5. So one rule about a factor tree is that we cannot use 1, okay, ever in a factor tree. So when we go to break something down, we can only break it down if it is composite, right? So if it has a way to be broken down other than just 1 times itself. So now I go to 3, and I want to break down 3, if I can. But when I look at it, I see that that is prime. So I can't break it down. So if it's prime, I'm going to circle it and end there. Same with 5. I go back up to 10. Is 10 prime or composite? It's composite because I can break it up. So 2 times 5, and I notice that both of those are prime. So I circle them. So this is not my prime factorization. This is the tool that I use to get my prime factorization. My prime factorization is a set or a little list of prime numbers. So my set or list of prime numbers is whatever I have circled. And we write it generally in order from smallest to largest, and we don't put commas between them. We put the little multiplication sign, the little dot, because I'm showing that if I multiply these together, I'm going to get 150. Let's check it. 2 times 3 is 6. 6 times 5 is 30. 30 times 5 is 150. The other way we can write this is 2 times 3 times, well, 5 times itself is 5 squared. Okay, let's look at this one other way. Let's start 150 again. And instead of doing 15 times 10, I'm going to do 2 times 75, which is another pair of factors of 150. Well, 2 is prime, so I'm going to circle that right away. 75 is not prime, so I'm going to split up 75 any way I can. I'm going to split it up, into 3 times 25. Well, 3 is prime, so I circle it. 25 is not prime, so I break it down further, which is 5 times 5, and I circle those because they're both prime. My factor tree looks different, okay? If you think about it as a tree sort of thing, this has like a short branch and a long branch. This has 2 that are pretty even. Just depends on how soon I get to my primes. Even though they look different, if you look at the answers, what's circled is the same prime factorization. 2 times 3 times 5 times 5. Okay, so it does not matter what you choose to start with or how you break things up along the way if there's more than one choice, as long as you are always making sure that you do pick a pair of numbers that are factors of that branch above. So I could have said 75 is 5 times 15. If you picture that, my 5 would have been here, 15 would have been 3 and 5. I still would have ended up with the same thing. Okay, so let's try prime factorization of 1,575. So I, off the top of my head, do not know factors of 1,575. But all I don't need all of them in this case. I just need a starting point, right? So I am going to say, well, because it is divisible by 5, or it ends in 5, I know it's divisible by 5. So I'm going to start like that. You don't have to. You could try other numbers until you found something that is divisible into that. But I'm going to divide by 5, and I find that this is 5 times 315 when I do that on my calculator. I do 1,575 divided by 5, and I get 315. This is a prime number, so I circle it. 315 is the other side. Again, I don't know what goes into that, but I do see that 5 goes into it. So to make it easy on myself, I'm going to do 5. I get 5 and 63. So 5 is prime. 63 kind of looks like it's prime, but it's not. If you think about your multiplication facts, it is 9 times 7. 7 is prime, so I circle it. 9 is not prime. It's 3 times 3. So my prime factorization is going to be 3 times 3 times 5 times 5 times 7. Sometimes just to make sure I get them all, I just count how many things I have circled. Here I have 1, 2, 3, 4, 5, and here I have 1, 2, 3, 4, 5. So hopefully you see there's another way to write this one also. So I have 3 squared times 5 squared times 7. Either one of those is fine. Okay, so let's go down now. The last page here, last 2 pages, are some vocabulary that you need to make sure you know. So the word sum is the answer when we add. The word difference is the answer when we subtract. And this is important too, because if we say, what's the sum of these two numbers? If you don't know what sum means, you don't know what operation to do. The product is the answer when we multiply, and the quotient is the answer when we divide. Okay, and some of these, especially on this page, are things that are going to come up when we are working on building equations, okay, when we're going from words to numbers. If we double something, we multiply it by 2. And if we say something is twice something else, it's also multiplied by 2, right? If someone got twice as many points as I did in a basketball game, then if I got 10, they got 20. I multiply it by 2. Triple is multiplying it by 3. Okay, now the next ones are a little bit tricky. So people kind of get them confused sometimes. If I have a square of a number or the square root. So if I say, the square root of a number, that's this, right? So the square root of 9, for example, would be the square root of 9, which is 3. The square of a number means multiply by itself. It means to have the exponent. So the square of 9 is 9 squared, or 81. Okay, so if it doesn't say root, it's the exponent. If it's squaring something, that's one thing. If you're square rooting, that's the other. Same idea here. So cubing a number, let's say the cube of 2 is 2 cubed, which is 8. The cube root of something, if I take the cube root of 27, that is going to be 3, because 3 times 3 times 3 is 27. Okay, and the last page here has some properties we're going to look at. And a lot of these we do all the time without thinking about it. So this one basically says we can add and multiply, I'll say or. We can add we can add in any order, and we can multiply in any order. Now, this does not take the place of order of operations, right? We always have to multiply before we add if we have a mixture. But this is saying if I just have 2 numbers, if I have 5 plus 3, or I have 3 numbers or whatever, but I'm just adding, I can do 5 plus 3. That's the same as if I do 3 plus 5. Okay, you do this all the time. If you go to the store and you pick up, a gallon of milk and it's $5, and then you pick up some cheese and it's $3. When you get up to when you're figuring out in your head how much you owe, it doesn't matter if you think of it as 5 plus 3 or 3 plus 5, it's still going to be 8. And same thing with multiplying. I can do 2 times 5, that's the same as 5 times 2, which is good because this meant you only had to memorize half as many multiplication facts. If 2 and 5 was not the same time as 5 times 2, you'd have double the facts to remember. Associative property has to do with grouping. Okay, so if I have 2 plus 3 plus 4, and I have this grouped, okay, so that means that I do this first. This is actually the same answer as if I had the last ones grouped. 2 plus 3 here is 5, and 5 plus 4 is 9. Over here, 2 plus 3 plus 4, 3 plus 4 is 7, 2 plus 7 is also 9. Okay, and that works for multiplication also. Again, if you just have multiplication, that works also. Okay, additive identity property. So the identity is who you are, right? So what can I add if I have any number? I'm just going to say a number here. What can I add to it to keep that number the same? Well, I can add 0, right? Any number I have, if I add 0, this keeps the number's identity. So I'll say adding 0 keeps the number's identity. It doesn't change it. Think about multiplicative identity, multiplying. If I take a number and I multiply it by something, what do I multiply any number by to keep its identity? Well, 1, right? So multiplying by 1 keeps the number's identity. Okay, additive inverse. This means if I add opposites, it equals 0. So, like, for example, 5 plus negative 5 is always going to equal 0. If you think about it, so opposites, again, are a number, and if it's a negative number, it's the positive of that number. If it's a positive number, it's the negative. If you think about how we drew it out, this would have 5 pluses and 5 minuses, and they'd all cancel each other out, right? Multiplicative inverse property means if I multiply reciprocals, it equals 1. Reciprocal, to find a reciprocal, I flip the fraction. So if I have 3/5 times 5/3, it's going to be 15 over 15, which equals 1. Or if I did the canceling, they would all come out to 1. Okay, 0 property of multiplication just means anything times 0 equals 0. And division with 0. Okay, if I take 0 over a number, that's going to equal 0. But if I'm dividing by 0, this is what we call undefined. Okay, or it doesn't exist. It's not allowed. We cannot divide by 0. Okay, so that's the end of Chapter 1 notes. I'm sorry for the little bit of technology issues here and there. These notes will be posted also. I'll send an announcement out about where you can find them. So you'll have the blank copy and the completed copy. Okay, so again, please, anything that you're not sure about, you can go back and watch the videos again. And then you can also bring questions to class this week, to my office hours, or just send me a message. Okay, thanks guys.